this video, we're going to look at states of change, so phase changes and how the entropy is affected by that. I'm going to go ahead and I'm going to draw the entropy of a substance here. Maybe I've got a mole of a substance, and I'm going to take the temperature here. And I know that there's a couple of important temperatures for substances above the triple point, but below the critical point, there is a melting point and there is a boiling point. And below the melting point, of course, we've got the solid phase. Above the melting point, we've got the liquid phase. And above the boiling point, we've got the gaseous phase. In the solid phase, the structure is nicely arranged. We've got a perfect crystal. In fact, if we have a perfect crystal at absolute zero, our entropy at absolute zero will be zero. We'll see that that is actually the third law of thermodynamics. And the reason for that is that there is only one way to arrange all the atoms in a crystal. So there's only one structure with that energy. So that's one microstate. And so if we've got one microstate and we take the natural logarithm of that value, we get zero. So at absolute zero, there's only one arrangement. As we increase the temperature, the atoms can wiggle around, so there's multiple microstates with exactly the same energy, and so we see this curve start to increase. And so I'm going to go ahead and just kind of draw it up like that. And then at the melting point, essentially the molecules are melting, so the solid form is less stable now than the liquid form, and we see a rapid jump in entropy. So as we're breaking those intermolecular forces, we're allowing the molecules to move. Now there's a vast majority of microstates available. Once it's all melted, as we increase the temperature, the molecules move with more and more kinetic energy. So there's more microstates, there's sort of more randomness if you prefer, until we get to the boiling point. And at the boiling point, essentially the molecules are being ripped apart from one another. They can occupy much larger volumes. There's way more microstates available. So we see an enormously rapid increase here. And then in the gas phase, as we heat up the gas, we increase more entropy. There's just more arrangements possible. In fact, the word gas comes from a Flemish word meaning chaos. The jumps here correspond to the entropy change. So this would be the entropy of melting or fusion. And this one here would be the entropy of boiling or vaporization. And we can see that the vaporization change is much larger than the fusion change because, I guess I didn't draw the atomic structures below. In melting, right, there's a little bit of randomness. It's a little higgledy-piggledy. But when you boil, right, essentially those molecules are very far apart. There's very many more microstates that are available to them. So there's a heck of a lot more entropy. And one little pro tip here, is that the entropy change on vaporization is massive. And in fact, anytime we make a gas, gases have massive amounts of entropy compared to solids or liquids. So later on, we'll look at reactions. And anytime we've got a reaction that increases the number of gas molecules, we will see that there will be a massive increase in entropy coming from this fact.